Thank you, Jen, and thank you all for sticking around when you would probably rather be eating lunch by now. So I'm not going to pretend that I'm clever enough to know which is the best ocean world to go and study to find life in the next human generation, but if you compare my age to the demographic of most of our presenters, you realize I have less time to spare than most of you, so I'm really getting quite antsy about it. And so that's really the motivation for what I'm going to talk about today is a new 5-year program that we're having funded through the NASA Astrobiology program. And it's going to be a big collaboration I'm introducing, and all these really clever people down the bottom here are all the people I've tricked into playing along with me. And standing next to them, I'm hoping I'm going to look really good. So that's basically what we're about, and it's really trying to come up with, trying to be planetarily agnostic. So rather than consider one planet at a time and work out how would you actually fit the data to make it look like a really compelling target, would be to start the other way around and say, okay, how about we just start with a blank slate and just say, taking the kinds of stuff that we know about. Let's assume we're not going to defy the laws of physics, chemistry, geology, and what we know about biology and how it could potentially work elsewhere. Are there places we could actually go to, or how would we come up with some value judgments on a like-for-like basis that would actually allow us to say, well, which ocean worlds and with which measurements would provide us with the highest probability to actually come up with a successful approach to go and search for life? And so to actually get beyond that first question, I think there's two really important concepts to come up with. This is thinking about not just about can a planet host life, but it's could a NASA mission, or anybody else's mission for that matter, go out and actually search for that life and come back with the compelling evidence that we want. So there's basically two components to this then. There's the biological potential, which is could planet X actually host life in the first place? Or to what extent could it host that life? Because it isn't just a binary thing. This isn't just a, is it plausible, is it credible? We're trying to go beyond that binary thing of, yeah, okay, maybe this one could have life, or this one looks deeply unpromising. It would actually be, what's the probability function? The kind of stuff we were hearing about in the plenary this morning of the probability of finding life. But then the second part is, even if you've got an ocean world that's probably teeming with life, if it's going to hold it away and keep it secret and make it impossible for us to actually find it, that's a whole other issue as well. So that's the second part of how you'd make those value judgments, is not just the potential to actually host life, but then the potential to reveal that evidence of life to the kinds of missions that we could imagine actually being able to field in the future. And so the way we want to do that then is basically, we've come up with a threefold approach. And the first part was actually going, my background is more in the ocean sciences than in astrobiology. So a first starting point that we could contribute was go and work out how do we harness as many of the smartest people that I've met over the last 30 years of my career in the ocean sciences and make sure we're actually folding all that information into what we do next. But then the second part is saying, okay, but a bunch of oceanographers wandering in and stumbling around the field of astrobiology uninformed could cause an awful lot of damage and not necessarily be very helpful. So how do we actually make sure that we have these people at every stage of the way in lockstep with planetary scientists who actually can turn around and tell us, well, that can't possibly work on planet X or planet Z or planet Alpha because there's these other things going on that we do know. We don't know huge amounts about other planets compared to what we know about our own planet and its system and how it works as an integrated system. But there are some basic things that we do know, so there's some things we can't violate, and so we have to have that right. And then the third part is what we've recognized is the team we pulled together to actually put this proposal together, we have to love each other dearly and trust each other dearly because we're going to be hammering on each other intellectually non-stop for the next 5 years. So we're going to be basically going out of our way to make ourselves uncomfortable. And so as we've chosen that, it's meant we've actually chosen quite a select, tight-knit group of who the PIs are going to be. And then the danger there is that you alias everything you do because you've just got some people's locked-in prejudices they bring to the system. So this is only going to work if you guys work with us as well, that this program is designed as well throughout to be community-led as well, or community influence. So we want to basically make sure that every step of the way we embrace as much as possible of the rest of the community. So let's get on to the naive oversimplification part of things. Over about 6 months as we developed the proposal, a dozen of us sat with a virtual whiteboard and we hammered on what are all the processes that you could imagine happening generically on a template ocean world. And what are all the issues you might have? We came up with a cartoon impression of, well, this is what could be happening just for the physics of an ocean world. And then on top of that, we layered on what could then be happening in terms of the geochemistry that would be begat by those physical processes. And then from that, what are the kinds of potential metabolisms that might be available for microbial activity and where might all those things be? And then by a deft sleight of hand, we worked out that we could actually reduce that back to this little Wi-Fi icon of here are the key 6 different investigations and what their interconnections might be. And so we have people with expertise at the center of each of these different investigations, but really where the real juice and flavor is going to come from this meeting is probably going to be more at those interconnections, at the interfaces of where these things all hive together. But what I'm going to do now is just run you through the core elements of what those different components are going to be. So the first part starting, so this is, I remember we're thinking about ocean worlds, so this is where my version of habitability is not the same as having to have liquid water on the surface of a planet. So although that's one version of habitability, mine includes chemosynthesis because I've spent the last 30 years studying that kind of stuff, so I know it's a thing. And I can't erase that part of my brain. So we're going to start from the bottom up. And so the idea then is what might be happening geophysically? What would it take for any given planet to either have or not have internal differentiation processes? And if that resulted, there are some important things that might come out of that. One might be what's the thermal flux that's available to drive any kind of seawater circulation. Another one might be what are the processes that might actually produce topography on the seafloor. Our planets, because we lack data, we tend to draw radially symmetric cross-sections of ocean worlds. And it's vanishingly unlikely that that's true, and it's really, really important that we don't suppress that stuff, which is actually true of our own ocean circulation models. I'll come back to that later on. So this is just one example of Christophe Sautin's work, some of the work he's been working on. He's one of the PIs on our project. And so this is some of these most recent work thinking about Enceladus as just an example of the fact of this isn't to say Enceladus is definitely one of the things that's going to be really compelling, but it embraces like the philosophy of the diversity of geophysical processes that might be happening on the planetary interior, which we need to accommodate before we go any further. A second thing is we've talked about hydrothermal activity, and there's the stuff that I've worked on all of my career is actually exploring for different kinds of deep sea hydrothermal activity and trying to prove that there isn't anywhere you can go, and if you search correctly, you can't find it. I think that was a triple negative, sorry. But anyway, if you're thinking about hydrothermal activity and you're thinking of a black smoker, stop, please. And if you're thinking of hydrothermal activity and you're thinking of lost city, stop, please. There's probably the kinds of diffuse flow or the kinds of important fluid flow that are present on other planets may be completely different from anything we've seen. And the majority of fluid flow on our own planet is probably completely different from anything you've ever seen on National Geographic television either. So for example, here's a cross-section from a cartoon of Andy Fisher's. He's another one of our co-Is from UC Santa Cruz, who works on where most of the fluid flow happens on our planet. And it's at very low temperatures. It's massive integration in terms of physics and heat, of volume, but it's not the most spectacular stuff that makes for good television videos. So that's probably not the stuff you should be thinking about. And an example of how unpromising a planet can be, and it might still host seafloor fluid flow, is one of the things we've actually realized as our discussions was if you took the moon, and nobody really thinks of the moon as being geologically active, our moon, if you put 2 miles of water on top of it right now, you would not be able to stop fluid flow happening because of the pre-existing topography. So basically, if the moon can have seafloor fluid flow, then it suddenly makes you realize, hopefully, that philosophically just about any planet, no matter how boring you think it might be, might still be able to host reactions that could produce water-rock interactions and geochemical results. Another one of the prejudices I want you to leave at the door is that you actually think you know where the best geochemical reactions are going to come from that yield the most energy. This is some very recent work from Everett Schock's imminent graduate student, Tucker Ely, is about to graduate. And so these two plots on the left-hand side is showing you what happens if you take all the world's mid-ocean ridge basalts, and so this is a very Earth-based study he's been doing, and showing you how exciting or how unexpected the results can be. It turns out if you want the maximum energy yield for this reaction up at the top here, let me go back. That isn't the laser pointer, that's the pointer. So if you want the maximum energy yield you can get from that, it turns out the most important thing in a redox active bit of rock is actually the aluminum concentration. Who knew that? Hands up if you already knew that. Okay. Julie said the same talk before, first hand from Everett. And then on the right-hand side is then saying, okay, well then if you take that, what's theoretically available geologically in terms of an abiotic organic reaction, and how could that be harnessed into microbiology, then the second part that comes into this is you can't just think about what the rock is, you have to think about what the seawater concentrations are going to be and what the seawater composition is going to be that you're interacting with. And so that's the second half there, that then the grey shaded fields show you that even if you had all the best rocks in the world and you wanted to be able to generate what the the fluid might be of the water-rock reaction happening beneath the seafloor, that the actual energy yield that's available as you then go into the redox reactions that come up when you let that stuff then erupt back into the ocean it's out of equilibrium with, is also going to be regulated by the composition of the ocean that it emerges into. Modeling is cheap, so that's the idea, is the theoretical modeling. We can run millions of these calculations over the first phases of this program, but we're also planning to back it up with a bunch of experimental work in the laboratory. This can be both testing the water-rock reaction stuff under geochemical laboratories, but then also actually testing with model organisms what the microbial yields might be of different metabolisms. As we identify what chemicals might be available and what's on the menu for lunch, then we can actually turn around and treat different microbes and actually do microbial experiments as well to see to what extent those different metabolisms get exploited. So we have a parallel program of experiments we're going to be doing there. That all gets us about as far as understanding the biological potential. We then have to go on to the biosignature potential for the same system, and part of that becomes, well, how would the ocean circulate on an ocean world? And here again, we're trying to actually bring together two different length scales of, basically this is a line of weakness in how we understand our own ocean circulation, that most global circulation models for our own planet, and this is we're using, working with John Marshall from MIT, who runs the three-dimensional global circulation model for Earth, one of the top-of-the-range models to get used for that. It's completely devoid of seafloor topography, even though we know seafloor topography is really important for mixing. So it turns out John's actually made a bit of a start on this because he's actually been starting to think about this. He's very much a climate modeler. He's been interested in snowball Earth, what was happening 700 million years ago. So we already have some preliminary models of what would happen in a completely ice-covered Earth's ocean, where you have an isothermal surface when you have the ice-water interface everywhere, and so circulation is driven primarily by haline circulation rather than thermohaline circulation, that it's basically brine exclusion would actually be driving global scale convection, because that's one end member, although another one could be if there's geothermal energy from below that's driving the circulation. So that's that kind of parameter space. But then we're also going to be working with Andreas Thurnher from Lamont, who's going to be putting some honesty into that stuff. He spends a lot of time thinking about how topography shapes circulation on local scale processes, both in terms of ice-water interface and at the seafloor. So that's what the couple of examples are here. There's a plan view of work down in Antarctica, of ice-water, rock or seafloor interactions, and then also at the larger scale of fracture zones, the fact that there are lumps on the seafloor, even if they're not volcanically active today. The last of the investigations is then going to be looking at the biogeochemical fate of materials in the oceans, and then I think one of the cleverest sleights of hand in our proposal, or I think that's really quite elegant, is the idea that particulate material in Earth's oceans, biogenic particulate material and mineral particulate material, has already pre-concentrated interesting stories for us. That compared to going and filtering large volumes of seawater and seeing what's dissolved in the seawater, then actually the mineral materials can actually tell you something about the processes that have already been happening in that ocean. And they also have the potential to survive. The stuff I picked up from the Europa Lander report was the idea that if you wanted to go and grind up your seawater and melt it and filter it, then you'd be in a good shape to actually go and look at some stuff. And then, of course, if you're thinking about places like Europa, then there's also what's the fate of that stuff once it gets out onto the surface, and how would it survive in irradiation? That if you had a mission that was actually just going to go and scrape the surface and look at stuff, how would that have been modified compared to whatever it was like when it left the pristine ocean? Sometime over the way, we're going to synthesize the whole thing and pull it all together. But just to wrap up, I want to show you that basically this is where you guys get involved. Basically, what we have is 3 phases over 18 months each. Over the next year and a half, we're basically going to go away and try and put together a conceptual model of how all those different parts would link together, and then we want to bring that back to a community workshop, and you can all beat the hell out of us and tell us what we've missed and what's missing. And then once we've done that, then we'll go and work out how to parameterize that and turn that into a forward model that can make millions and millions of forward calculations. That'll be the second 18-month phase. And then the third part, which is the really critical part, is how do we do the sensitivity analysis? We can make billions of predictions based on no knowledge whatsoever, but just like a flicker roll of the dice. I would predict that most of those different combinations of parameter space will come out looking really barren and boring and unproductive. And there'll be a tiny subset will be the places that actually tell us where the juicy results might come from. And if we can get all that done in the next 4.5 years, that'll give us 6 more months to actually prepare a lookup table for the Europa Clipper mission, and we can be nice and NASA relevant. So that's really, and the mechanism we actually want to do for all of that is through this new Network for Ocean Worlds. So if you come along this evening to the town hall, Alison Murray, who's a co-lead of that with me, and Alyssa Roden will be there to tell you all about that. Okay, thank you very much.